Alright, I think it's working.
Okay, so here we go. We're going to do lesson 8 now. Woo! Thank you. Everybody think see how fun my E-hour is?
We clap up every.
Okay, we already had our 20 minutes of banter, so we're not going to do that again. All right, so lesson 8. Oh, I need to clean up notes and put out the other ones. All right, so I know all of you had plenty of time to read lesson 8, since I told you about this morning. All right, so in this is only 2 sections. It's pretty small. So what we're going to talk about now is, since we got the chance to talk about alcohols, now we're going to talk about making ethers. So the big thing is, we're going to talk about some of the stuff we talked about last lesson, which is reacting alcohols to make ethers. So the first way that they talk about making ethers is using some sort of alcohol and then using an acid. So some of you, we just talked about this, but others, we'll get to it a little bit more. So in essence, we're going to react the same thing with itself twice, using some sort of acid, and then we're going to get the ether. That's kind of the overall reaction. And the problem here, well, let me go through the reaction, then we'll talk about some of the limitations. But really, what we use is the acid. Actually, it's better to use something like sulfuric acid. So let me change the acid. Because when we have the chlorine there, we have the chance of doing the substitution as well. So let's say sulfuric acid. All right, so as we've said many, many times, sulfuric acid is strong acid, which means it's going to do what? Dissociate and/or give up its proton, right? Or one of its protons. So in this case, we're going to have the alcohol act as the base or the nucleophile. Going to pull off that hydrogen. And we have a good leaving group now. Now that we have a good leaving group and there's plenty more oxygens or alcohols where that came from, the next alcohol, which is a good nucleophile, is going to just do a substitution reaction, SN2 type, and we're going to get the ether. That'll kick off and make water. In this step over here, we made HSO4 minus. So that's the easiest way as far as mechanisms go to make an ether. The problem is that this isn't the best way to make an ether for several reasons. One, we have a big competition between this type of reaction going with the substitution reaction and elimination reaction. So you can have the elimination compete with the substitution. So that's a problem if you're only looking for the ether product and you end up getting a substitution product. And as a matter of fact, the book shows you that. They show you if you have the alcohol, even using the same acid, sulfuric acid, I think it's only a difference of like a few degrees, like 40 degrees, 180 degrees and 140 degrees Celsius. And you get, here you get the alkene, and then here you get the ether. So it's really close. So this isn't always the best way of doing it. So usually lower temperature is better. And usually you can only use the primary alcohol. So that's another. When you get to secondary, tertiary, you get the elimination level.
So the mechanism of that, when we made the ether.
Oh yeah, I
Where's the
skipped a
second-
step, right?
Yeah,
So
where does the second pair come from, like lone pair?
it's gonna be like this instead,
Okay.
positive. And then the sulfuric acid, or the HSO4 minus or water can grab off that proton. You just want it to have more mechanisms in it.
I did.
There you go. No, that's good to complete the mechanism is really that way. Good point. In an acidic environment, you're always going to have that exchange. You're going to be proton center. Very easily accessible. And the other limitation here is you can only make symmetrical ethers. Because you can imagine, when you get to this step, if we had a different alcohol in here, now we have a lot of combinations of possibilities. If we put in some other alcohol here, you could have this reacting with itself, this reacting with one of these, or two of those reacting, so you're going to get 3 or 4 products possible. So symmetric is the only way to go. So this is one way of making ethers, not the best way, a lot of limitations, right? So of course, there's some smart chemists that figured out other ways that are a little bit better, which usually require some other reagents and stuff. And that's what we're going to kind of talk about now. Everybody got all this? So another way to be better at making ethers is to use what they call the Williamson ether synthesis. So what happens there is we take the alcohol, react it with something like sodium amide, or not sodium amide, sodium hydride, excuse me. As we showed in the last problem, the hydride takes off the proton, and you get the alkoxide. The sodium will be the counterion, and you create H2 gas, which goes away. So now that we have the alkoxide, we have a really good nucleophile, and then you can react it with a good leaving group. So whatever this reacts with, say you just put in the alkyl bromide, you get a substitution reaction, and you get the ether. Okay, the good thing is this doesn't have to be the same ether or the same alkyl group. So just maybe for illustration purposes, let me put an extra wing on there. So there's an extra methyl group there. So now we can make an unsymmetrical ether if we want, just as long as we have some sort of alkyl halide or some sort of alkyl leaving group. So they suggest a few other ones in the book. They say bromine, iodine. They show some of the ones that we talked about before with the sulfonates and the sulfates, which we talked about before, making a good leaving group with the oxygen. You can have them here, and they'll be able to leave pretty good. So Williamson ether synthesis is just using the alkoxide with an alkyl halide or a good leaving group, and you get the synthesis of an ether. Here, you don't have as many challenges as you had with the acid catalyzed. The only problem is that the best results are usually primary. So usually use the primary, and then it goes to secondary, and then tertiary alkyl halide. So this substance here, if you get to tertiary, it doesn't work out so well. But primary, secondary is the best way to go. If you get to tertiary, a lot of times you get the elimination product. So this is Williamson's way of making ethers. The good thing is you can make, you can make it unsymmetrical. Does that make sense?
Yes.
Any issues? Pretty easy. What's that?
By not reading the section, I would say stuff
Let's say that. Boy, I hope they can hear what I'm saying on the video. That's pretty far away. Oh, well.
There's no sound to show.
Just narrate it afterwards.
Yeah. All right, everybody got this? So the other way is to use the oxymercuration, demercuration. So we've done some of that before, right? But they introduce a little bit of a different reagent. This time it's, so this is, so this one we use so it's a new mercury one, but you can use a mercuric acetate too, which we've used before. What ends up happening here is, if you remember from a while ago, we can get it to dissociate where we have CCF3. So this would be plus, and then we have O2 CCF3 minus. So now that that dissociates and we introduce an alcohol into this, or actually a double bond. So this one is, instead of oxymercuration, we call it alkoxy, I should say. Alkoxymercuration. So the end result here, to kind of back up, is we're going to take a double bond plus an alcohol with the and then we use sodium borohydride to, once they react together, then we're going to get basically the double bond. So we get that 1, 2, and then O, 1. So a good example, well, the one that they use in the book is just a double bond here, ring. So once we have this positive charge, now the double bond will go out and attack that. So we get an attachment of the mercury, and it actually kind of forms a little triangle. There's electrostatic attraction all the way around. All right? Yes, NABH4 and then OH. So once we have that kind of combination there, then the alcohol can come in, whatever our alcohol is. Can attack, kick that off, so that we have okay, and then we use, as we did kind of the first semester, we don't necessarily show you the magic behind the sodium borohydride. The base will take off the hydrogen here later on, and the sodium borohydride replaces this with a hydrogen. So the end result here is the that's gone, and you have you've made the ether again.
And so, I noticed that there you actually get like as far as
Here? Yeah, so if you want to talk about stereochemistry here, what you get really is, say we can make this solid and this dash, because this, as we talked about, I think last semester, this oxygen is going to have to come from the backside because the mercury is occupying the top side. So they're going to be different. They're going to be different stereochemistry. But it's just going to. This is just going to come off as an H. But you already have an H on there, so that won't make too much of a difference. Okay, so that's the alkoxymercuration, demercuration. Does that make sense? We can do something similar with that now to kind of make protecting groups. So the next section really is protecting groups, and that talks about using T-butyl ethers and silyl ethers. That's what we talked about a little bit last when we were doing that wheel before. So if we were to use an alcohol and we reacted it with, so what is that compound? It's 1, 2, 3 propyl. So it's a propene, methylpropene, right? So 2-methylpropene. So if we react those two together in the presence of some acid, what ends up happening? What does the acid do to the alcohol? Make a good leaving group, and then the double bond will be a nucleophile and do the attack, right? So what ends up happening is we get ROH2 plus. That kicks that off. Oh, actually no. Hold on. Got lost with that. Once we get the, we have to keep that, we have to keep that on there. Or that'd be wrong. It's not the same mechanism. Yeah, I don't know. It's not the same mechanism here, but the end result is, I have to think about it, is we get the terp-butyl.
So this still.
So this has to be like that. And then this will have to take the hydrogen. So it goes like that in some way, shape, or form. Don't have to know the mechanism of it, but realize that we're going to get a protecting group there. What's the question?
This is still part of the same process, right?
Well, it's kind of it's a different example. Yeah, so this is something new.
So is this still alkoxymercuration?
Nope, we're not using mercury at all.
That's okay. So okay. Does this have a name? Or?
No, this is just a way to make a protecting group. I mean, they call it the terp-butyl ether by alkylation of alcohol. So the reason why this is important is, say, if we had an alcohol and a bromine on the same molecule, and we say wanted to react it with, remember our triple bonds, right? That would be a good nucleophile, and that would attack. Well, if we want the desired product, what we want is this. That's what we want, but that's not what we get. That doesn't happen. What actually happens is and that picks up the hydrogen basically. So that's a problem. If this is what we want, well, we end up getting this. Right? So the way around that is to protect the alcohol. So we protect the alcohol, we take this, we react it with this and some acid, and we get the protection. Then we react it with the alkyne anion. It'll do now it's going to do a substitution reaction here. We get the desired product, and then we just have to use some dilute acid to remove the double bond or the terbutyl. And we get the desired product of it. So we have to use protection sometimes, especially, and I know when I use examples, I usually use small alcohols, but this is the type of stuff you run into a lot more, especially like biochemistry or whatever else. You have a bunch of substituents on the rest of the molecule, and you have to be selective in which one you want to react with. So this is one protecting group that you can use. So I know, Patrick, you're wondering, well, what if I wanted to do this reaction in an acidic environment?
Really love that.
I knew it. And what if I had to do it in an acidic environment? It's just going to fall back off and I wouldn't be in all the problem, right? There's a way around it. That's using the silyl ether protecting group. So let me give you a second to finish this up and then we'll look at the silyl ether.
What was this one just called?
Just terbutyl.
Yeah.
Yeah, you can. Terbutyl ether. All right, we good? All right, so because Patrick was really worried about this, we're going to go into what happens if we have to use an acidic environment. So if we had an alcohol, so this one is going to be the silyl ether. So I spelled it wrong. Silyl. This is as a protector. Mark it down. So if we use an alcohol, in this case, you're using this silicone that has two methyl groups attached to it, and then it has a T-butyl attached to it, and a chlorine. So just like before, we talked about, anytime you have a big element towards the lower on the periodic table, it can accept electrons really well. So the electrons that are here can attack the silicone and keep out the chlorine. And now we have a protecting group there. Now, they also show imidazole and DMF. So at this point, they take off the hydrogen and the chlorine, so that you just have you're right, I should have. So now we have a protected alcohol, and the good thing about this is it doesn't just fall off with any old acid or base. You need to use what we call TBAF, or, so this is tetrabutylmodium fluoride. So what it looks like is, so the butyl, so this is Bu, F, and F, and it's plus minus here. So if you use what they call TBAF, they usually have TBAF is usually in CHF, and we get back to the alcohol. So the good thing about this is you have a very specific reagent to take off the protection group. So you don't have to worry about whether it's in an acidic or basic environment and losing your protection group as you go through it.
Is that BU like butyl?
Yeah, so what I mean it really looks like is so this is plus.
What does it say about THF?
What's that?
What does it say about THF?
THF, this is Bu 4 N plus F minus, which is that, which is a lot easier written as that. So, and it's even easier to say TBAF than tetrabutyl ammonium fluoride. But you should be able to figure out tetra means 4, butyl, and then ammonium is the N, and then fluoride. Ammonium is the N plus ion. It's not just squiggles, it's specific 4 carbon chains.
So what's the TBAF?
What's that?
What's the AF?
Ammonium. Ammonium is the
Oh,
N plus, and fluoride is the ion. So that's a specific way of protecting a alcohol without having to worry about the conditions in which you're going to do the next reaction.
but so TBAF is the same as BU for.
This is equal to this. Yeah.
Okay. So that's such a large.
Bu4 N plus F minus. So that's the advantage of using the silyl ether as a protectant. You have a very specific way of taking it off. Oh my God.
So the entire thing is to protect our OH, or is it just like that last part is just like everything?
What's that?
I'm a little confused with it.
So you put the silica, the silyl ether, you make a silyl ether by reacting with the silica compound. We got this. The imidazole and DMF ends up taking off the hydrogen and cleans up the chlorine so that you just get this. Then this can then react however we want, you know, whatever on R, we can do a reaction on the R, whatever it is. And then when we're done with that, we can take off the silyl part and make it back to an alcohol. Remember, R, you know, just like in that last reaction, if we had bromine and hydrogen, or hydroxide, we would have a problem, we'd have a competing reaction with two sites. This way, we can protect the alcohol, do the reaction on the opposite side, and then take the alcohol back off. That's the whole point of protection. Protecting. Good? Pretty easy? All right, last part. Now this is a mechanism in which you are responsible to be able to do, which is the cleavage of an ether by, so now that we made ethers, we're now going to break them apart. So it's really not that different than, it's just a reverse. So we have our ether and we have our acid. So as we've been doing this before, what is going to happen here? We're going to take off that hydrogen. Okay, we're going to have Br minus. So now that we have Br minus, we have a good nucleophile and we have a pretty decent or positive looking electrophile. So now what's going to happen?
Bromine will take off the oxygen.
So bromine, well, it's not going to take off a hydrogen. It could, I guess, and then go back to where we were at. But really what we wanted to do is attack that carbon and kick off that. So what we get is an alkyl bromide and an alcohol. But we're not done yet. Go ahead, what were you going to say?
Oh, there's the air going back into the oxygen?
Well, it's going to attack the carbon next to the oxygen, and then the electrons that were between the oxygen and the carbon are going to go to the oxygen. So, and we have 4 electrons. Okay, we're not done yet though, because there's a lot of acid floating around. So what can happen in this scenario?
It could create a water.
Yeah, you're just skipping a step. The first thing happens is the oxygen takes the hydrogen. We're going to create a good leaving group, and then we have bromine created. That's going to do a substitution reaction, and we're going to create another alkyl bromide, and we end up with water there too. So the net result is the ether with at least 2 equivalents of the acid is going to give us 2 alkyl bromides plus water. That's the net result of what's going on here.
You don't make 2 equivalents
What's that?
would it be 2 of the, oh, here it is.
Yeah, so we have, the products are here, here, and here. So all it is just a reverse of kind of what we talked about before. But this is, like I said, a mechanism that you probably required, or you are required to the lesson plan, lesson sheet. Okay, what are your questions on this?
Why do we have to use the protecting for the seals,
Saddle ether?
silo, ether, and acid? Like what?
Protects it.